Hi, here we go. These notes are for class tomorrow. I want you to make sure that you write down these formulas, and tomorrow in class we're going to go over how to use them. We just spent a couple of days on inverse trig derivatives, so these antiderivatives come from there. Now this is the first one, and it's going to look really scary, but let me take you through where it comes from. The inverse sine formula we know is 1 over the square root of 1 minus u squared du. Now sometimes you'll have, in complicated problems, you'll have fractions and things like that. Rather than do those complicated problems and explain how to do the antiderivatives, we're just going to give you this formula. Okay? And how you do a problem like this would be something like this. 1 over the square root of 4 minus x squared dx. We would look at this problem and say, okay, u is equal to x, because notice the positioning, whatever's after the minus sign. A, which is always a constant, is equal to 2. Now you might be like, no, you made a mistake. No, a squared goes in front, so a is equal to 2. And very nicely, du would be equal to dx, like we don't have to worry about coefficients, which means this integral will be the inverse sine of x over 2 plus c. That's it. That's how you use these problems, or these formulas. Here's the inverse tangent formula. We know that if we're doing the inverse tan of u, the derivative of that is 1 over 1 plus u squared. Well, if for du, if there was like a 3 there or something, that would affect this answer and lead us to the formula you see above. Now make sure you have that written down. And then let me show you a problem. The integral of, let's do 9 plus 4x squared dx. We go through these problems just like we've done before, doing a little u sub. A is equal to 3. Now u is equal to 2x. U is always the variable. That's the thing to remember. A is always the constant and u is equal to the variable. Now we're going to do a quick little du. So du is equal to 2 dx. So we're going to have to put in a 1/2 du in for that dx. But as long as we do that, this turns into 1 over, let's do this as a squared plus u squared times the 1/2 du. And the 1/2 comes out front. 1 over a squared plus u squared du. So that's 1/2 inverse tan of, let me back that up a little bit. The 1/2 comes out front. Now this part of it here, look at this integral right here, has an integral of 1 over a inverse tan of 2x over a plus c. So you'd multiply the 1/2 through and get 1/6 inverse tan of 2x over 3 plus c. We don't have to worry too much about the a. We just want to do a little u sub and make sure that we account for all the pieces. Here's the inverse secant version. And what I just noticed is that I forgot to put the du in up here. So just throw the du in there. Now let's look at this problem down here below. If we look and see what lines up, remember, the variable will always be u. So if I start off looking here, I'm like, oh, that's nice. U is equal to x, du is equal to dx, and a is equal to 5. The constant is a squared. So this turns into a nice little du over u root u squared a squared, which is exactly the formula. So that would be 1 over a, and I'm actually just going to write these numbers in. So it would be 1 over, 1 over 5 inverse secant of x over 5 plus c. So just look in your notes and just make sure your formulas are correct. Make sure your inverse sine formula is correct. Pause this if you need to. And then here's your inverse tan formula. And here's the inverse secant formula. So tomorrow what we're going to do is learn how to work with these and do some practice problems tomorrow and some practice problems on Wednesday. Reviewing on Thursday, silent bonus on Friday for a quiz on Monday. All right, I'll see you tomorrow. Bye-bye.